Welcome to our group garage. In this video showing the radial probability distribution, or where we really think we'll find electrons in an atom's 3p subshells. Our last video showed the three familiar dumbbell-shaped orbitals associated with an atom's 2p electron. The red 2px orbital on the x-axis, the green 2py orbital on the y-axis, and the blue 2pz on the z-axis. We have modeled our electrons as waves, solutions to the Schrödinger equation. With this, given the same center or the z number for an atom, we expect the 3p subshell to be larger than the 2p. However, remember, as was shown with the s subshell, the 3p electron distribution is not just a larger version of the 2p orbitals. We will get the specific difference in a moment, but first, shown here is a wave. Where is the mass? Where is the electron? As a solution to a wave function, we honestly do not know the exact location of the mass of the electron until we measure it. Like before, our measurement collapses the wave function and reveals the electron particle with mass somewhere within the region of the wave. For the 2p electrons, the wave function starts at 0, and so we have a node or nodal plane at the origin, near the atom. As the radius increases, the likelihood of finding the electron also increases, but then begins to taper off as we continue further away, eventually getting to approximately 0. Now, the 3p. What will that look like? Recall, each time we increase the principal energy level for the s subshell, the wave function crossed the 0 line one more time, and as such, there was a 0 probability of finding an electron at that radius. There was a node. Each principal energy level increase adds a node. Here is the wave function for the 3p subshell. Similar to the 2p, this wave function starts at 0, so we have the same nodal plane near the center of the atom. But with our wave function again crossing the line, either switching from positive to negative or negative to positive, either way, we'll have another node. So first, let's just look at one orbital. Here we have our red 3px orbital. We start with the wave function, we square the function to get the electron density, then we integrate or multiply by the volume related to the radius, and we get the radial probability distribution. Again, because switching positivity does not change the wave structure, the wave outline we will show actually looks exactly the same as the 2p, again just larger. It is really as we begin to measure our electron location, and we collapse the wave function that we begin to see the difference. Measuring more and more electrons, the familiar p subshell dumbbell pattern appears, but this time we can make out there's two different node regions and two different populated regions. The nodal plane located at the center of the atom, and a new one a little farther out on the radius. Obviously, as we move away from the center, the nodal plane turns into a spherical region, similar to the sharp or s orbitals. As we begin to look for electrons in other orbitals, first is the 3py. This wave function is similar to the 3px, and the difference, which is in the magnetic quantum number, just gives a different direction or orientation for the orbital. The 3py will be at right angles to the 3px, but the pattern for electron distribution will be the same. For the third and final orbital, the 3pz, this orbital again is orthogonal to both the 3px and 3py. But again, the same pattern appears. A node near the center, an electron-dense region, a second node at a radius where the wave function crosses the axis, and then more electrons. Here is the 3p electron shell. 3 separate orbitals, all at right angles to each other, and with a spin up and spin down, there can be 6 electrons in this subshell. Remember, each time the wave function is 0, there is a node, and each time we look at the next or higher principal energy level, all the orbital wavelengths will have another node. Here is the wave function for the 4p electrons. Note the 3 0 spots, 3 nodes. Following the same procedure, here's the radial probability distribution. As we measure the location of many electrons, here is what the distribution will look like for the 4px orbital. We will leave the p subshells here, but as you think about this, see if you can draw out the radial probability for maybe the 5p orbitals. And as we move on, possibly to the D subshells, we hope to see you in that next video. Hit the thumbs up if you found this video helpful, and for more, consider becoming a subscriber. If you'd like to support more projects in our group garage, I'd appreciate it if you use the link in the description to buy me a coffee. Thanks.